Welcome to lecture 22. Today we will be continuing with the remaining portions that we were discussing in the last lecture, that is more properties about the ring of Gaussian integers, trying to understand the prime elements of Zi. So last time we were discussing about this theorem and we proved that 1 implies 2, 2 implies 3. So today I will start with 3 implies 4 and then I will show that this 3 implies 4 and then I will last time I proved 1 implies 2, 2 implies 3 and 3 implies 4. Today I will prove 4 implies 3 and 3 implies 1. That will complete the proof of this theorem. So let's start the proof with that statement 4 implies statement 3. That means here I will be assuming that P is equal to 2 or P is congruent to 1 mod 4. In that case, I will show that this equation x square congruent to minus 1 mod P has an integer solution. So let's see. So today we will start the proof that 4 implies 3. So if P is equal to 2, then it is clear that 1 is a solution of that equation. So if P is equal to 2, then 1 is a solution of the equation x square congruent to minus 1 mod P. So we will assume now that P is congruent to 1 mod 4. So now let that P is not equal to 2 and moreover P is congruent to 1 mod 4. And we will prove in this case also we have a solution of this equation. So first I will claim that in this multiplicative group Z quotient PZ cross, we know already that this forms a group with respect to all the non-zero elements in Z quotient PZ, forms a group with respect to multiplication. So first I will prove that this has a unique element of order 2. So first claim is that this group contains an unique element of order 2. So in the proof of this statement, we will be using some of the group theory that you have already learned in some group theory course. So if needed, I will just recall some of the results whenever it is required. So I will just prove that there is a, since this order of this group is P minus 1 and 4 divides P minus 1, that means of course 2 divides P minus 1. So 2 divides the order of a group, that means there exists an element of order 2, and here we will try to prove that there exists a unique element of order 2. So let us start with an element of order 2. So let M be an element of order 2. So let M belongs to Z quotient PZ cross is an element of order 2. So that means that M square is identity, right? So that is M square is congruent to 1 mod P. So this implies that P divides M square minus 1, but M square minus 1 I can further factorize and write it as M minus 1 into M plus 1. So P divides M plus 1 into M minus 1, P is a prime integer. So this implies that either P divides M plus 1 or P divides M minus 1. So this implies that if P divides M plus 1 means M is congruent to minus 1 mod P, and if P is divides M minus 1, that will imply that M is congruent to 1 mod P. So this is nothing but if M square is identity, then I can see that M have two choices, either M will be equal to the identity element. So, identity element, its order is 1, of course. So, and I or it has to be equal to -1. So, we see that there exists a unique element of, there exists only one element of order 2 in Z quotient PZ cross, and that is nothing but -1 in Z quotient PZ. So, here we have proved that therefore, -1 is the unique element of order 2 in Z quotient PZ cross. So, this is the only element of order 2, that the residue class corresponding to -1 in Z quotient PZ cross is the only element of order 2. Now, the hypothesis says that P is congruent to 1 mod 4. So, since P is congruent to 1 mod 4, this implies that 4 divides P minus 1, and this order of this group Z quotient PZ cross is nothing but P minus 1. So, 4 divides P minus 1 order of the group. Then what we know by Sillo's theorem? Sillo's theorem says that, so 2 divides P minus 1. So, it will have all the subgroups of order P to the power, 2 to the power k. So, therefore, we can conclude from here that this will have a subgroup of order 4, since 4 divides P minus 1. Therefore, by Sillo's theorem, Z quotient PZ cross has a subgroup of order 4, say H. So, H is a subgroup of Z quotient PZ cross of order 4, and what do we know? How many subgroup, how many different types of group of order 4 are possible? There are only 2 possibilities for a group of order 4. Either it will be the Klein 4 group or it will be the cyclic group of order 4. So, hence either H is Klein 4 group or H is isomorphic with cyclic group of order 4, which is cyclic group of order 4. So, either H will be isomorphic with the Klein 4 group or cyclic group of order 4. But in Klein 4 group, we know there are 3 elements of order 2. But in Z quotient PZ cross, we have seen there exists only a unique element of order 2. That means H cannot be isomorphic with Klein 4 group. That means H has to be isomorphic with the cyclic group of order 4. So, we know that in Klein 4 group, but Klein 4 group has 3 elements of order 4, whereas the Z quotient PZ cross has an unique element of order 2. I am extremely sorry. This has 3 elements of order 2, whereas this has unique element of order 2. Hence, H is isomorphic with a cyclic group of order 4, is isomorphic with cyclic group of order 4. That means there exists an element of order 4 in H. So, thus there is an element A in Z quotient PZ cross such that A to the power 4 is identity in Z quotient PZ. So, which implies that A square is congruent to minus 1, sorry, mod p, because these elements we are choosing from Z quotient p Z cross. So, this is mod p. So, this is mod p. So, therefore, we can see from here that this has a is the solution of this equation x square congruent to minus 1 mod p. So, the element of order 4 is the candidate which is the solution of this equation. So, this completes the proof of 4 implies 3. Now, in order to complete the circle, next we will prove that 3 implies 1. So, what was 3 and what was 1? Let us just quickly go back and see what was 3 and 1. So, here you can see that 3 was the assumption is now that this has an integer solution, and we will prove that in this case pi is a Gaussian, this factor of p will be a Gaussian prime. So, that is what our next goal is. So, next I will be proving that 3 implies 1. So, in order to prove that, first you note that I have this isomorphism. So, note that Zi is isomorphic with Zx quotient x square plus 1. How this isomorphism is? So, you can consider this map from Zx to Zi. How this map is defined? Consider any polynomial fx and evaluate it at I. So, I am just replacing x with I. So, suppose this map is phi, okay. Then what will be the kernel of phi? Kernel of phi is all elements such that iota is a root, and the smallest degree polynomial such that iota is a root is nothing but x square plus 1, and you can show in this case that the kernel is nothing but the ideal generated by x square plus 1, and this phi is in fact a surjective ring homomorphism. Therefore, by first isomorphism theorem, you can say that by first isomorphism theorem, it is clear that Zx quotient, the kernel which is generated by x square plus 1 is isomorphic with Zi. So, this is the proof of this fact that Zi is isomorphic with Zx quotient x square plus 1, and I will be using this in order to prove the statement. Now, I would like to see that if I am having that if I am having that x square minus 1 has a solution, in that case this p can be p is reducible. So, that is what we would like to show. So, let us see what is this Zi quotient p is. So, Zi quotient p is isomorphic with, so Zx quotient x square plus 1 quotient, then I can write it as nothing but p comma x square plus 1 quotient x square plus 1. So, this is again isomorphic with nothing but Zx quotient p comma x square plus 1, and which is again isomorphic with, I can see that this is isomorphic with Zx quotient p and then p comma x square plus 1 quotient p. So, this again I can rewrite it as Z quotient pzx quotient, this is x square plus 1 bar. So, this 1 bar is nothing but the image of 1 in Z quotient pz. So, you can see here again the next observation is that this Zx quotient, the ideal generated by P in Zx, this is isomorphic with Z quotient Pzx. So, how do you prove this statement? You can consider the map from Zx to Z quotient Pzx by, say, consider any polynomial, say a0 plus a1x and so on plus anxn, and you send it to this a0 bar a0 bar plus a1 bar x plus an bar x to the power n. So, this bar denotes the image in Z quotient Pz, and so if this map you are denoting by phi, then you can in fact show that kernel of phi is nothing but the ideal generated by P in Zx. Therefore, by first isomorphism theorem, again you were able to show that this will be an isomorphism. So, this is just for the reference. So, now let us go back to the main proof. So, I have shown that Zi quotient P is isomorphic with Z quotient Pzx. So, now Z quotient Pz is a field. So, this is a polynomial ring over a field and I am having x square plus 1 bar, but we know that x square congruence to minus 1 has a solution. That means this x square plus 1 bar is no more an irreducible polynomial over this polynomial ring. That means this is no more an integral domain. That means P is no more a prime element in Zi, and hence P is no longer an irreducible element. So, let me just state it. So, since x square plus 1 x square is congruence to x square congruence to minus 1 mod P has an integer solution. So, that is equivalent saying that x square plus 1 bar is reducible polynomial in Z quotient Pzx. Therefore, P is not a prime ideal in Zi, hence P is not an irreducible element. P is not an irreducible element in Zi. So, if P is not irreducible, that means P can be written as product of irreducible elements. So, let P can be written as P equal to pi into delta, where pi is an irreducible factor of P. That means pi is a Gaussian prime. So, now I am able to write down P as pi into delta. So, then if I apply the norm on both sides, then I will get that norm of P is nothing but norm of pi into norm of delta. But what is norm of P? Norm of P is nothing but P square. So, from here what can I say? Pi as an irreducible element, therefore, norm of pi will be equal to pi into pi bar, which will be equal to P only, because here P is not irreducible and pi is an irreducible factor. That means delta is not an unit. So, note that here delta is not a unit. So, therefore, delta is not a unit, that means norm of pi have only one choice, that is it has to be equal to p. It cannot be equal to 1 because it is not an unit element, because it is an irreducible factor of p, and it cannot be equal to p square also, because if norm of pi is p square, then it will force that norm of delta has to be equal to 1, then delta will be a unit element. But if delta is unit, then that will say that p is irreducible, but p is not irreducible. Therefore, I am able to write down in this case that this p can be written as pi into pi bar, where this pi is an irreducible factor of p, or pi is a prime, Gaussian prime. So, this completes the proof of this theorem. So, this characterizes this, since this is an if and only if condition. So, this in fact characterizes all the irreducible prime integers in Zi. So, let me state as a corollary. So, the first corollary is important in number theory, which is known as the Fermat's 2 square theorem. Fermat's 2 square theorem. So, what does it says? So, it says that let p be a prime integer, let p be a prime integer, then p is a sum of 2 squares, then p is sum of 2 squares, sum of 2 squares, if and only if p equal to 2 or p is congruent to 1 mod 4. The proof we have just seen in the previous proposition. So, this is one of the famous theorem in number theory. In the number theory, you can see there are different proofs, but this proof we are using the technique of ring of Gaussian integers here. And as a next corollary, we will be identifying all the irreducible elements of Zi. So, the irreducible elements, of Zi are as follows. So, what are the irreducible elements of Zi? So, first of all, 1 plus iota and all its associates are irreducible elements, because if you check the norm of 1 plus iota is 2, and we know that if norm is a prime number, then it is a Gaussian prime. So, 1 plus iota and its associates are primes. So, this is because it has norm 2, which is a prime number. Then the prime integers p, such that p is congruent to 1 mod 3, because if p is congruent to I am extremely sorry, p is congruent to 3 mod 4. P is congruent to 3 mod 4, because we know that if p is congruent to 1 mod 4, in that case p is not a prime, and that was if and only if condition. So, p is congruent to 3 mod 4, then it is irreducible element. And last one is that a plus ib and a minus ib, the distinct irreducible factors of this prime integer p, which can be written as sum of 2 squares for prime p in Z with P congruence to 1 mod 4. We have already seen that if P is congruence to 1 mod 4, in that case P can be written as pi into pi bar, where pi is a Gaussian prime. So, therefore, if P is congruence to 1 mod 4, then its irreducible factor is again a Gaussian prime. So, that is how we have identified all the Gaussian primes in the ring of Gaussian integers. Now, with the help of this characterization, we will be able to describe the factorization of an element in Zi as well. So, how do you do the factorization, write down the factorization of an element in Zi? So, now we can write down the factorization of an element in Zi. Factorization of an element in Zi. How do I write down the factorization? So, just let us understand with the help of an example. So, let us see the example that we are trying to understand. So, suppose I am having this number 35. So, 35. So, 35 is an integer. So, first what we will do? We will write down the prime factorization of this integer into product of prime integers. So, 35 can be written as 5 into 7. Now, this 5 and 7 we will see whether they are Gaussian primes or not. So, what criteria we will use? Here we can see that 5 is congruence to 1 mod 5 is congruence to 1 mod 4 and 7 is congruence to 3 mod 4. So, this implies that this 5 is congruence to 1 mod 4, that means 5 is not a Gaussian prime. 5 is not a Gaussian prime. Whereas 7 is congruence to 3 mod 4, that means 7 is a Gaussian prime. So, 7 is because it is irreducible. So, and irreducibles are prime. So, therefore, it is prime. So, that means I cannot factorize 7 further, but I can factorize 5. And how can I factorize 5? So, 5 can be factorized at pi into pi bar. And you can see this 5 can be written as 2 plus iota into 2 minus iota. So, 2 plus iota into 2 minus iota into 7. So, this is how I am factorizing this integer 35 into irreducible in product of irreducible in Zi. So, first you factorize the integer into prime factorization in Z, and then you look into the primes which are irreducible in Zi and which are not. Those which are not irreducible, then you further factorize it in Zi and write down the factorization in this complete factorization in Zi. So, in the next lecture, we will be trying to understand which integers can be written as sum of two squares. So, I will stop today, and these are the references that I have used for today's lecture, and thank you.